Right, good afternoon everybody. Welcome to this lesson on exponential growth or exponential modelling. So, if you're studying at Bilborough College, many of you will have come across exponential modelling before. Everybody should have seen logs and exponentials as well when we're...
Welcome to this lesson.
Oh God,
Exponential
I have to deal with that echo. Just give me a second.
So, if you're studying at Bilborough College,
That's better. Sorry about that. Right, back to where we were. So, many of you will have met exponential growth before, so some of you may be doing different work to others during this lesson. I'm expecting that everybody will have done some work, but maybe some people won't have got very far in terms of practicing exam questions and things like that. So I'm just going to give a quick summary of everything we're going to go through before and then go back to the beginning and start properly. Okay, so first of all, this week's work, if you're a Bilborough College student, you can access everything you need from parkermaths.com/year 1 maths and then go to week 25. Anybody else, if you're not a Bilborough College student, you can still access most of the same stuff if you go to parkermaths.com/remote learning, and then you want the week 2 tasks, which are broadly similar. There's just not quite as much there. Okay, so exponential growth then. Previously, you've hopefully seen solving log equations, and we're going to use that knowledge now to look at exponential growth and decay in this lesson. And then next lesson, we're going to be looking at reduction to linear form. So, we're going to start off with a few practice questions. There are 6 questions to go through. They're just solving log equations, which is something you probably started a few months ago. If you're in one of my classes, you will have actually done these set of 6 questions, and so for this part of the lecture, instead of, you can do these again if you want, there's no harm in practicing them, or you might want to have a look at some of the exam questions later on and just make a start on a few of those. After that, we're going to look at a few transformation questions to make some links between graph transformations and exponential growth. So it's just a little bit of curve sketching, and for each curve you're going to be looking at the transformations. So there's a few questions on that. After that, I've got a couple of, we're going to be just looking at exam questions because I think that's what most people will need to practice. So I've got a couple of ones that I'm going to model, a couple of example problem pairs for you guys to have a go at. And then after that, I've just put a set of 6 mixed exam questions that increase in difficulty as they go along that I want you to spend about 40 to 60 minutes on later in the lesson. Now, that doesn't mean that your teacher will expect you to have done all 6 questions. It will probably take you longer to do that. You might want to use your judgment a bit about which questions you do. Questions 5 and 6 are a bit more challenging than the other ones. Each question as you go along has got some hints in. So if you look at the question and you get stuck, say for example here part A, if I click that, it'll give you some ideas about how to attempt that question. And there's a hint for part B here. After each question is a mark scheme, and you can view the parts separately. Some questions have got written solutions, some questions have got mark schemes. It depends on whether I thought it was necessary to add something to what's on the mark scheme. Question 5 is more difficult than the other ones, and question 6 is very difficult. Not many people get this right first time around, particularly towards the end of that question. So if you're very confident with exponential growth, please make sure you have a go at that question. Okay, so I'll go back to the beginning then. So, what I would like you to do is, if you've not seen these questions before, have a go at the 6 questions that are in the PowerPoint on exponential growth. If you have seen these before and you think they're too easy, then feel free to skip ahead and have a go at a couple of the exam questions while you're waiting for everyone else. So I'm going to give you between 10 and 15 minutes to have a go at these. Although there are solutions there, it might still be that you don't understand the working out for one of these questions. If that's the case, please do send me an email and I'll annotate one of my solutions and I'll go through it in more detail. But if nobody tells me they're struggling with something, I don't know. As well as that, please do email in if you spot a mistake anywhere. I do get a couple of people to proofread them, but the PowerPoints are very long and they've got a lot of maths in them, so there's inevitably going to be mistakes for people to spot. Okay, so 10 minutes then, maybe 15. Have a go at these. Please keep me updated. If you find that you're nearly finished, let me have an email so that I know when people are starting to get to the end of them. Okay, off you go. Okay, like last time actually, before people start, I'm just going to quickly flick through the answers on all of them as well, because I know some people occasionally have difficulty opening the PowerPoint. So if you don't want to see any of the answers, please do look away now while I just quickly flick through the answers. Okay, what I could do with now then is we've just spent 10 minutes on them. If you could just find me a few emails through so that I know that roughly where people are up to. The more people that send an email, the kind of wider spread I'll get of where people are up to. I'm guessing that people might need a little bit more time, but if I get emails from everybody and they're saying no, we're nearly finished, then we'll obviously move on a bit quicker. So just let me know. Which question you're up to, for example, and if you're having any difficulties, if people tell me which ones they've struggled with, I can obviously go over a couple of things. Something I would like to point out, when you're doing some of these questions, be careful about the level of accuracy you give. So in question 1, for example, 2 decimal places, fairly obvious, 3.63. Question 2, though, it says find the exact solution. It's really important when you see the word exact in a question that you're not using your calculator with logs, because most of the time most logs will evaluate to decimal approximations, particularly this one. If you do log base 2 of 7/8, you'll get a decimal, and that means your answer is no longer exact because it's just an approximation that you see on your calculator. So when you see exact, leave the log in your answer and just rearrange to get x on its own. Okay, the reason in question 2 there's 2 answers is because you may have solved this by taking log of base 2. If you take log of a different base, say log base 10, you get a slightly different answer that's equivalent. Right, so I've had a few emails through now then. Most people are either on 5 or 6 or just about finishing. I'm only going to give people another 2 minutes in that case because the actual log equations, although they're useful to be solved, they're not as important as the exponential questions in questions 1 to 4 in terms of what we're going to be doing today. So another couple of minutes, then we'll move on to the next bit. Right then, just before we move on, I'm just going to go over the end of question 5. When it doesn't disappear anyway. Okay, so just a couple of things about this one. In this equation, you've got 2 log terms and one that's not a log term. What we want to be looking at doing is combining together all of the terms that have got logs in. So in the first step, we bring the power up so that we get 4x squared. Remember, it's all of the 4x squared though. Leave the 2/5 on the other side. Then we can expand out that bracket and we can take these 2 logs now and we can combine them to make a single log using the subtraction rule. Okay, then we've got log 2x equals 2/5. Remember, when we just have log like this means log of base 10. And so what we're doing from here, we're writing this log in equivalent form. So when you write a log in equivalent form as a power, whatever the base of the log is the base of the power. And then these 2 things essentially switch places. So it's going to be 10 to the power of 2/5 equals 2x. And then we just divide through. We can't simplify 10 to the 2/5. We leave it as is. Just divide by 2 and we get half times 10 to the 2/5. Okay, moving on then to look at what we're going to do today. Like I've said previously, today's lesson is more of a recap lesson for a lot of people. I'm assuming that you're confident with the kind of questions we've just done, and I've not had that many people emailing through, so that seems to be true. I'm also assuming that you might have seen a few of the kind of questions we're going to look at today as well. If you haven't, don't worry, you'll still be able to follow along. You just might not be as confident with some of the stuff we're going to do. Okay, so solving log equations is essential. Bit of modelling, it will be helpful if you've done that before. So, quick recap about what the different things mean. In this equation here is an exponential growth equation. In the equation, the thing on the left hand side is the amount of something you've got, the amount of bacteria, the amount of money, the amount of radioactive atoms, whatever it is. The value of A is however many you start with, so at t equals 0. And then the value of K is something called the constant of proportionality, and that tells us how fast the quantity that you're measuring is growing. The bigger the value of K, the faster the thing is growing. And T in these equations generally stands for time. Now we've got a value of E in here. Now that doesn't necessarily have to be E. It could be, E remember is a number, it could be any number in there. Quite often though we do deal with E in exponential growth equations because it's easier to find rates of change because we know how to easily differentiate E to the power of something. Okay, one other thing to point out, the power, or the index as you're supposed to call it really, if it's positive, so in this case it's kt, assuming that k is positive, that would imply we've got an exponential growth. If I stick a minus sign in front of that power and make it negative, that would indicate that we've got something that's shrinking. We'd have exponential decay. We're going to get less of it over time. So, what I'd like to do now is make some links between graphical transformations and exponential growth. Okay, both topics you've seen before, but you might not have seen some of how they relate to each other. So I'm just going to give people, say, 20 seconds now. See if you can just do a very quick sketch of the graph y equals e to the x. Okay, the only thing I want you to mark on there is where it crosses the y-axis. Okay, don't worry if you get it wrong, you can always cross it out. Just have a go. Okay, hopefully you draw something like this. Okay, now this is going to be our starting point for the next few questions. We're going to start with a standard exponential curve. This is e to the x, but it could actually be anything, and you draw it just the same. It could be 2 to the x, 5 to the x. As long as it's a number bigger than 1, that number to the power of x will have a curve that looks like this, going through 1 on the axis. Okay, typically when we are dealing with exponential growth equations, when we're modelling, time is going to be on this axis, and the number of whatever it is will be on this axis. Okay, obviously it's y and x here, so they'd be x and y on your graph, but when we're doing modelling it will usually be t and n or some value like that. And consequently, because we don't have negative time, we'd only have this little bit of graph after here. This bit of graph would be meaningless in that context. Okay, so what I'd like to think about now is, on the next 4 pages, what do some of these graphs look like? Now, you don't have to create masterpieces when you're sketching these. Very quick sketches will be fine. All of these equations here, on the next 3 slides, are all graph transformations that you can get from e to the x. So what I'd like to do for each one, first of all, see if you can sketch what this graph looks like using e to the x as your start point, and then think of it in terms of a graphical transformation. Now, the reason I want you to make this link is because, for example, on this one, e to the minus x, this will be what an exponential decay equation looks like. And by looking at the graph, you can get a bit more of a big picture about what's going on when we get to some of the exam questions later. So there's various different ways we can write exponential modelling equations, and I want you to have just seen the graphs of a few of them to start. So I'm just going to give you between 5 and 10 minutes just to have a bash at drawing some of these. As we get on to question F, G and H, they actually require you to do 2 transformations, which is something that's covered in the second year. However, you might be able to just use your common sense based on what you already know about graph transformations and still figure them out. They're not tricky ones that are designed to catch you out. Okay, so 5 minutes to have a go at those then. Okay, let's take a look at some of the answers from here and how what the significance is with these and when we do some exponential modelling. So e to the minus x then should be a reflection in the y-axis. So in the context of when we're modelling things, we won't have this bit of the graph here below t equals 0, but what we can see is it increases more steeply to start off with and then it decreases more steeply to start with and then slowly tails off towards the end. And as the time approached infinity, we would approach 0 for that one. Minus e to the x is just a reflection in the other axis. In terms of exponential modelling, you wouldn't really get minus e to the x on its own. You could get something where you move it up by a bit as well, so we could translate it up to do something with that. Question C is quite a typical exponential growth one. We have a number out here. Quite often as well we'll have a number in next to the x. That's a stretch scale factor 3 in the y direction, which means our starting value if we're modelling would be 3. So whatever number we have here, if we only have one term, this will be our start value. Part D is a translation of 4 upwards. Okay, so we'd start at 5 and would be increasing here. This curve, it's probably useful to point out, wouldn't be as steep as this one here in the long run, because we're multiplying by 3 on this one. Okay, right, E and F, this one is another one we're stretching in the x direction this time though, and F is probably the one that first is starting to look like we would have if we're exponential modelling. Okay, so 7 would be our constant of proportionality and 6 would be our initial value in that one. Okay, and question H is probably one that's relevant to some of the harder questions we may look at. In this one, it's 5 plus e to the x, 5 plus e to the minus x, which means we'd have a start value at 6. Because it's got a negative in the power, that means it's decay, so it's decreasing, but it's not going to go down to 0 because it's been translated up by 5. You could draw a horizontal asymptote across here at 5. So a typical thing you might be asked in a question that has an equation like this is, what happens as the time approaches infinity or gets very large? In which case, as the time approaches infinity, we're going to approach a y value of 5. Right, okay, so I'm going to go through a couple of exam style questions now. These questions have got a lot of the things in that you would typically be asked to do in the exam. All of these questions are actually taken from year 13 papers, so they're directly relevant to the kind of questions that you're actually going to have to answer when you're in the real exam rather than in an AS exam. Okay, so I'll just give you a minute or so to read it. Okay, so here is our exponential decay equation this time. M is the mass in grams, T is time in years. Okay, so let's just first of all think, what will the graph of this look like? It could be helpful in understanding the problem. So it's similar to some of the ones we've already got. We've got a negative power here, that's going to be a reflection, and the 40 means we're going to have a stretch. So if we were to draw it, we'd have something like this. Okay, I've got rid of this bit here because that's not relevant. We're going to start with a mass of 40 grams. That's going to be the initial mass. And then it's going to go downwards like this towards 0 as time approaches infinity. Okay, so in the first part of the question then, we're going to find the time taken for the mass of the substance to decrease to 25% of its initial value. So if we look at our equation here, we know the initial value is 40. So 25% of its initial value would be m equals 10. Okay, so all we're going to do to solve this first part then is substitute m equals 10 into this equation, and then we're going to use logs to find out what t is. So let me just copy our equation down to start off with. We've got m equals 40 e to the minus 0.132t. And we're going to say when m equals 10, because that's when it's at 25% of the original, we're going to get 10 equals 40 e to the minus 0.132t. And then we're just going to solve this equation. Dividing both sides by 40, 10 divided by 40 is a quarter. And that's going to give us e to the minus 0.132t. Now, something that's worth pointing out here is that we didn't actually need to know what the original mass is to find the time it takes to get to 25% of the original. It's actually irrelevant what the original mass is. It will always take the same amount of time to get to 1/4 of the mass. So in some equations, even if you didn't know what this number is here, you could still work with this. If this was like a letter, say A, you could put in here 1/4 of A. And you quite often have to do that to find something if you don't know what the initial value is, if you don't know how much of something you've got. Anyway, we'll carry on solving this equation. We're trying to find a power. That tells us to take logs. Because we've got e to the something, we're going to take natural logs of both sides. So that gives us natural logs of a quarter. The natural logs will cancel out the e to give us minus 0.132t. And then here, we're just going to do log of a quarter divided by minus 0.132. And it might look here like something weird's going on because you're dividing by a negative, and you might be thinking, well, that's not going to make sense because I've not got negative time. But if you think carefully about logs, you'll realise that log 1/4 is actually a negative number. If you think about the shape of a log graph, it looks like this. This value here is 1. Anything between 0 and 1, when you take the log of it, you're going to get a negative value out, a negative y value down here. So it will be a negative divided by a negative. Another way of thinking about it is that log a quarter, using the log rules, is log 1 minus log 4. And log 1 is 0, which means that will disappear. So log quarter is actually the same thing as minus log 4. So that's another reason why you can see that it's going to cancel out. The answer you get here is 10.5 years. Okay, let's take a look at part B then. So in part B it says find the rate at which the mass of the substance A is decreasing when t equals 5. A key word to look out for in this part of the question is rate. If you see the word rate in an exponential question or in more generally in most questions, the rate of change of something means you want to find the derivative of that quantity. So if we want to find the rate at which the mass changes, that means we want to find the derivative of m with respect to t. So going back to what we've got here, here's our original equation we can use. We'll just copy it up here. M equals 40 e to the minus 0.132t. Just give me 1 second, I've got an email. Could be that I've made a mistake. Nope, on this occasion it's not. Oh, I messed that up. Okay, so what we need to remember here is the rule for differentiating an exponential. So if we have e, let's say e to the kx, or e to the kt in this case might be better, and we want to find the derivative of that. Okay, unlike when it's x to the power of n, we don't reduce the power. The power stays exactly the same. Okay, and that's partly because of the definition of exponential growth, that it's proportional to the original amount. So our answer will contain e to the kt, but we have to multiply by whatever is in here. So we end up with k e to the kt. Okay, so essentially all we do, we keep the e part the same and we multiply by whatever's next to the t. Now there is a reason for that. You learn about it in year 2. It's something called the chain rule, but for now we just have to take it as a rule that we need to be able to apply. So dm by dt is going to be minus 0.132, so I'm multiplying by this bit here, times 40, which is already there, and then the e part stays the same. Okay, now if you wanted to at this stage, you could simplify this. I'm not going to bother, I'll just do that on my calculator in a bit. And if we just quickly go back to what it's asking us, it's when t equals 5. So we are going to evaluate the rate of change of t, which is dm dt, at t equals 5. All that means is sub in t equals 5. So minus 0.132 times 40 e to the minus 0.132 times 5. And if you pop all of that into your calculator, you end up with minus 2.73, and the units, the mass is measured in grams, and time is measured in years, so this is grams per year. Okay, key thing to point out here, the most common mistake people make in these kind of questions is they sub in the t equals 5 before they've found the derivative. It's really important that you differentiate first, then you sub in the value that you want. Okay, I think on this question as well, if you look in your PowerPoint, the units are wrong on this question and the next question. The units here are grams per year. Okay, finally we've got part C to do then. So, substance B this time, so we've got a different substance, is decaying exponentially. It says initially its mass was 40 grams, and 2 years later its mass is 31.4 grams, and we're going to find the mass of the substance after a further year. So essentially we're going to be finding the mass after 3 years. Okay, so this question is going to require us to do a little bit more for ourselves. So we'll start with our exponential equation. It said the initial mass of this substance was also 40, so I'm just going to pop a 40 in there. Because it's a different substance, it will probably decay at a different rate. So rather than having minus 0.132, we're going to pop a k in up here. We're going to write down an exponential decay equation. Okay, then we're going to use the initial conditions. It said after 2 years, the mass was 31.4. So by substituting in these two values, we can find out what is the value of k. So we're going to get 31.4 equals 40 e to the minus 2k. So I've subbed in t is 2 and m is 31.4. So if we divide that through, 31.4 divided by 40, I worked it out earlier and I got 0.785. And that's going to be e to the minus 2k. Similar to in the last part, take logs of both sides. Okay, and into our calculator then, we're going to put log of 0.785 divided by negative 2. Again, this is going to be a negative divided by negative, which gives us k equals 0.121. In general, in these questions, k will always be a positive number, and whether it's growth or decay, you'll deal with that by whether you have a minus sign in front of the k up here. So what we've got now then is m equals 40 e to the minus 0.121 t. Okay, it's worth noting though here, this value here is not exact, and when we're doing these questions, I want you to store it in your calculator. I'll just show you how to do that in case you're not familiar with it. So the calculation we've done is, get rid of all these other ones we've done, log 0.785 and then divide that by negative 2. What's going on there? Ah, sorry, my mistake. I did the wrong log. Natural log of 0.785. That's why I prepare the answers early. Is divided by negative 2. This is this is a better approximation of that. If you want to use a value later on in a calculation, the way to store it on your calculator is to press this arrow button here. Okay, it says answer is going to, and then I'm going to press alpha and A. So I'm going to store this value as A. And then at any point later on, if I don't change that value, it will always be stored on my calculator under A. Okay, technically you can use the answer button to get previous values, but that will only get you the very last calculation you did. Whereas doing it this way is better in some ways, because it means I can use that value if I've done another 5 calculations. Okay, so we wanted to find the mass after a further year, which we said was when t equals 3. We're going to get m equals 40 e to the minus 0.121 times 3. So how I would do that with this value stored in my calculator, I would do 40 e to the minus, and then I will go alpha a, and then times that by 3. If I do that, that's 27.8 to 3 significant figures. Okay, so that's a typical exam style question with various different parts in it. If you need to have a look through the PowerPoint, it's a neater version than the one I managed to write out. And then I'd like you to have a go at question 1p. It's 6 marks, so we'll say I'll give you 10 minutes and we'll see how we get on at that point. We might need a little bit more depending on how people are feeling about it. Okay, so something to look out for on this one as well is part 2. It's slightly different. You're still finding a rate, which we found before, but there is a shortcut to part 2, which I'll talk about when people have had a chance to have a go at it. Okay, so 10 minutes, off you go. Okay, we've had about 10 minutes then. I'd really appreciate it if a few people just shoot me an email. Let me know whether you've done, whether you're still working on it, so I know roughly where people are up to and whether it's time to move on. I'll go through the answers in after that though. Okay, I've had quite a few replies coming through saying that people have done, so we'll move on. We'll have a look at the answer then. So, the first thing that you might not have spotted, even though you still got the correct answer, was this little bit that I've written down at the bottom here about the mass doubling every 33 hours. Now, you didn't need to do that. There was another way of doing it. It's pretty standard to get the t equals 33, which is 33 years. That's when it doubles. And to do that, you subbed in 500 here. To find 8 times the initial mass, you could simply have subbed in 2000 here, done a separate calculation, and you would have got this answer out, which is 99. But one of the properties of exponential growth could have actually allowed you a little bit of a shortcut, because the time that this mass takes to double is always the same. The mass, the actual start mass, or whatever the mass is at any particular time, is completely irrelevant. It will always double in the same amount of time. So after 33 years it will be double, and then after another 33 years it will have doubled again, so it will be 4 times the mass, and then after another 33 years it will have doubled again, and so after 99 years it will be 8 times its original mass, because it doubled, and then it doubled again, and then it doubled again. Okay, so that was a little shortcut. If you've got that deeper understanding of exponential growth, you'd be able to use. Okay, part 2 then. Again, the way that I've written it here might not be the way you thought to do it, and that's okay at this stage. You might not have seen the shortcut. What you may have done instead of my method here is you might have differentiated and got this bit here, and then you could have said, well, what can I do? Because you'd have had a t in your equation here, and you might have said, well, when my mass is 400, what would my time be? So you could have subbed 400 into this original equation, figured out a value of t, and then you'd have a value of t to sub in here. You'd get the same answer as what I've got. Just a little note, this is a mistake that 3 people have told me about. Well done for that. My original PowerPoint didn't say grams per hour in there. The units were wrong, so I've corrected that since, but yours will say something different. Okay. The shortcut though is to know that whenever you differentiate an exponential, you always get the original value in your equation. Okay, so the trick is to not simplify this bit here, because when I differentiate m, I end up with a 0.021 at the front, but the rest of the equation is just what I originally had for m, so I can swap that for m, and that means I don't have to go all the way around the houses finding t. I can just sub in 400 for m and get to my answer. So that's a shortcut to look out for whenever you're dealing with exponential growth, is that when you differentiate, the original thing is still in your equation. Okay, so I've got one more example for us to look at. This one is a little bit different. It's got k in here instead of e, Okay, so it's just something to the power of t. So I'll give you a few seconds, just have a read through the question, and then I'll have a go at it and I'll talk you through the answer. Okay, let's have a go at the solution for this one then. So this one's about the weekly pay of a footballer. So P is the pay in pounds, and T is time, which is measured in years. Okay, so first thing we're asked to do is write down the value of A. Now you can do some working out here, and find we know that initially at t equals 0, which is the 1st of August 1960, the pay was 80. But we should know by now, hopefully, with exponential growth equations, that if you've only got one term here, the initial value will be whatever you're multiplying by here. So we should hopefully be able to write down that A is the initial value in this case, which is 80. Okay, so you could do some working out. There's some working out in the PowerPoint which shows where this came from, but it does just say write down, so we can simply write the answer down in there. Okay, in part 2 it says show the value of k is this, correct to 6 decimal places. To find this, we're just going to use the other condition in here. So it says by the 1st of August 1985, it's risen to £2,000. So, if we substitute in these two values, we'll be able to find out what k is. But we need to think a little bit about what we're going to substitute in here first. So 1985 is 25 years after wherever we started here, which is the 1st of August 1960. So the value of t we're going to substitute in is 25. So what we have here is when t equals 25, the weekly pay is £2,000, which isn't a lot compared to what football players get paid nowadays. So if we substitute those numbers in, I'll just write our equation up at the top. Here we've got P equals A times K to the T. We're going to start with P equals 80 times K to the T and substitute in our values. So we get 2000 equals 80 times K to the power of 25. And if we do a quick division here, divide both sides by 80, 80 into 2000 is 25, so we get 25 equals K to the 25. Now this next bit is one that catches a lot of people out in these kind of questions, which is why I've included it, because automatically when people are doing exponential growth, they resort to using logs to solve things. Now logs are very good when you want to find the power, but they're not so good when we want to find the base. If we've got something to the power of 25 and we want to undo that and get back to k, then what we really need to do is the 25th root. So we're going to do the 25th root of 25. So that's not 25 multiplied by that, that is the 25th root. Just in case you're not familiar with how to do that on your calculator, I'll show you. It's the button that's above the power button. If we press shift and that button there, we get a box to put our root in, so 25th root of 25. Okay, and that gives us 1.137411, which is what we want here. Okay, because I'm probably going to need to use that k later in the question, again I'm going to store it, so I'm going to put the little arrow in, and then I'm going to overwrite the last time I used the value a, just there. Okay, so I can use that value on my calculator if I need it now. So, next part then, it says use the model to predict the year in which on 1st of August the average weekly pay of a footballer at the club will first exceed £100,000. So, what we're going to do is figure out what happens when the pay is £100,000. And we could consider that to be our critical value, because after that the pay will be increasing, so it will go up and it will be higher than that. So what we've got is 100,000 equals 80 times k to the power of t. Remember, k is this number down here. I'm just going to put 1.13 and use an ellipse there. I'm going to use the exact value in the calculation, to the power of t. Dividing through by 80 gives us 1,250. Okay, this time around I am trying to find the power, so I do want to take log. So I'm going to do log of 1,250 equals log of 1.13. Now I could, if I'd have wanted, have done base of that number there, but I'm just solving this a different way because it can be quite confusing to use unusual bases to some people. I'm going to bring the t down using the power rule, so I'm going to get t log 1.13 equals log 1250, and then I'm going to divide through to get t equals log 1250 over log 1.13. And if I put that into my calculator, I get 55.38. Okay, I'm just going to come back to that in a second. Somebody's pointed out a mistake I made over here. I was supposed to be substituting in 25 at this point. It's right on the next line. This shouldn't be 2t at this point. This should be 25 over here. So sorry about that. Okay, so now we've got this value of t. This is how many years it's going to take. So it's going to take 55 and a little bit. Now if we do 1960 and we add on the 55.38, that gets us to 2015.38. Okay, but remember what this 0.38 stands for here. This is after August the 1st, because that's where we started. Okay, so if we just added on 55 years, that would get us to 2015, well, August the 1st in 2015. But that wouldn't quite have been enough time to get us to £100,000. We'd still need to get this extra little bit of time on. Okay, and because the question specifically asks us when on the 1st of August, the year on the 1st of August where it will exceed that, okay, then we need the year to be one more. So we're essentially rounding the year upwards. And that's because when we get to the 1st of August 2015, the pay still hasn't reached 100,000. If you're not sure, one thing that you could do, you could say, I'm not sure if it's 2015 or 2016. You could sub those values of t back into the original equation and find out what values of pay is. And you'll find that one of them, if you sub in 2015, you'll see that it's not big enough. And then when you sub in 2016, you'll see that it is big enough. Okay, so that's one way of checking your answer there. Okay, so here is a similar kind of question for you guys to have a go at. Okay, I'll go, the solution's in the PowerPoint, but I'll go over some of the details of it in about 10 minutes. Okay, I'm going to guess that people have either finished this one or pretty much finished it, because it was very similar to the last one. Part A, 1 and 2 are very similar. You're doing the same kind of thing. The only thing that generally would catch a few people out on this one is what to do with their answer, whether it should be 56 or 57. So if we look at the question, it says write down it dropped below £5,000 during the nth month, and you might initially think, well, 56.89, so it must be the 56th month. But if you think for a second about when the first month would be, that would be if you had a value of t equals 0 point something, and so it's kind of shifted by 1. So when you really get an answer of 56 point something, it means you've gone 56 months and you've gone 0.89 into the next month, and so that's why the final answer to this is 57. Now, I realise that we're almost at the end of the hour and a half, so there's no obligation after another 10 minutes or so for anybody to have a go at these. But I'm just going to talk through the different exam questions. Hopefully people will still want to have a go at a few of them. You don't have to do all of them by any means, but it's not like we can really go anywhere at the moment, so maybe you'll have a little bit of time to do them. Okay, so question 1 has quite a lot of hints in. The maths involved in this question is relatively straightforward. It's probably easier than some of the questions you've done so far. The difficult thing in this question is interpreting what you have to do, which is why I've put these 2 hints in there. So in this question, before you start it, make sure you read it really carefully and you understand what's going on. Okay, if you do that, you'll have a better chance of answering it. Okay, question 2 is very similar to one of the ones we did in the example. In this question, the first part is bog standard finding a mass. Second one is to do with the rate of change. If you look at the answer to I think it's 1p, it's very similar to what we did in that. So if you found 1p easy, maybe skip that one. This question here about the vintage car is very similar to the one you've done a minute ago. So if you found that one easy, that might be one that you want to skip. Or if you didn't find it easy, probably a good one to have a go at. Then question 4. The first part is relatively straightforward. The second part, however, is a little bit more difficult. So if you're finding things easy so far, this might be a good one to have a go at. The key thing is to do with reading the question carefully. It says find the time when both of the substances are decaying at the same rate. That word at the very end is key to answering this question. I thought this one was quite tricky when I looked at it, so I've done an actual solution for that one for you to follow along with. Following on from that, the next 2 are kind of more extension questions. This one is not too bad, but the algebra involved, it does get a little bit tricky at times, particularly dealing with powers. And in my opinion, question 6 is very difficult. It's one that's kind of only for the brave, really. In particular, the last 3 parts, especially at the very end, the very last part, are pretty challenging. The solution in the mark scheme runs to 3 pages, so I couldn't copy it into here. You can click on this link to load the mark scheme, or there's also somewhere, it's not a great video solution, but it's better than nothing. There's a video solution if you do have a go at that one and get stuck, particularly with the very last part. Okay, so feel free to ask me questions at the end of the lecture. If you're still struggling with it, just send me an email. Ideally, if you've done some of the work, it's helpful for you to send that through. I can quite easily write on top of any PDF you send me and then send it back with some annotations to help you out if you get stuck and you're not sure what's going on with the mark scheme or the written solution. So what I'm going to do now, I'll give you 5 minutes to have a go at those. At the end of this lecture at 3 o'clock, feel free to go if you want to. A couple of people have asked me some questions about the circles part on the Dr. Frost homework, in particular questions 7 to 10. Now, I'm not going to sit here and do all the questions, but what I will do is I'll display them on the screen, and I'll talk through them a little bit and give you some ideas, some pointers about how you might approach those questions. Okay, so thank you for watching, and hopefully we'll see you on Friday.